This is the fourth video in the series Basic HVAC, written and presented by me, Jean Legui. Here's the legal staff. I want to talk to you about variable air volume boxes. What these are small insulated boxes with a butterfly valve inside them, called a damper. You open and close the butterfly valve, the damper. You open and close the damper to let more or less air through the box. One side of the box is being fed, the inlet is being fed from the air handling unit, and the outlet is going out to the room. You have an airflow sensor, normally a pitot tube of some description. And what the airflow sensor does is it senses the airflow. It actually measures air speed, let's be honest. It's measuring the velocity of the air. And from the velocity of the air and the fact that we know the diameter of the duct, you can calculate the airflow. So you open and close the damper to increase or decrease the airflow through the VAV. You stick an actuator on the shaft, you stick a controller on the whole thing, you stick a temperature sensor in the room, call that the space temperature sensor, and we're good to go. We're now able to control rooms to an individual temperature. There's two main types of VAV. The first type on the top left, the big silver thing, that's the style I've been describing, where you have a damper which opens and closes the duct to let more or less air through. At the front left there, you can see the airflow sensor, the pipes with the small holes in them. Two pipes are coming off from that, two pressure sensing pipes, a red and a blue, and they're going into the orange thing, which is a Belimo controller. That's got a little motor on it, you see, and the shaft coming through so that it can move the shaft left and right, or clockwise and anti-clockwise. Next to that, the box, the other silver box with the isolator on it, that's the controller for the electric duct heater. The other type of VAV uses a plug which goes in and out of a seat in the duct. I'll get a pointer. So, there's the plug. It's a cone-shaped plug, and it moves left or right to insert or come out of the duct. It moves left or right because it's on a threaded shaft. The threaded shaft is moved in and out by an electric motor, and it moves the cone in or out of this piece of duct. I don't like these VAVs very much. I've not had good experiences with them. Firstly, they're very, very slow. They take 5 minutes to go from fully open to fully closed. Secondly, in certain positions, they sing like organ pipes, and that's not very good. Here's a parallel fan. Fan's in a different place. So while it doesn't mess up the airflow sensor, you still get the whole thing with the cockroaches, fiberglass and rat shit. Here's a parallel fan with pulse width modulation. Yeah. Now what to do in a fire? What do VAVs do in a fire? Now there's various things, there's lots of functions that VAVs can do. One of them is pressurization and one of them is depressurization. Normally in a fire what we do is we just turn all the air conditioning off. There used to be traditionally this idea that we shouldn't feed the fire, we shouldn't give it oxygen to burn. So we turn all the air conditioning off and we close all the dampers. Now this, by the way, is why it's really important that we not have an outside air damper with the last louver open. What we can do in a fire, which is even better, is we can do what's called sandwich pressurization. Okay, with sandwich pressurization, we basically pressurize the surroundings of the fire. So we switch off the supply air fan to that fire, and we switch the return air fan on full so that we're sucking out from the fire. Where the fire actually is, we've got suction, so we're sucking out. Because the danger in a modern fire isn't the flames. The danger in a modern fire is the smoke and the fumes from all the burning plastic. You will be dead from the fumes long, long, long before you are burned. So we suck all that smoke and all those fumes out of the building. Either side of the fire, we pressurize. We blow the air into that building as hard as we can. That way, any smoke is blown into the section with the fire. We also pressurize the stairs so that no smoke gets into the stairwells and the emergency exits. When we're doing this pressurization, we have to be extremely careful that we don't over-pressurize areas, because if you over-pressurize something, you can't open the door. So we have to make sure that we test the doors so that they will open. There's specific scales and ways of testing this. I would recommend you go to your local building codes to find out what pressures you need to be able to open the doors. And with sandwich pressurization, everybody not in the area where the fire immediately is will be getting fresh air and no smoke. And hopefully they'll get out. Before I go, I want to quickly talk about chillers. Chillers are refrigerators that cool water, and we use that cool water to cool the air. So we generally have in a building, unless it's a brand new building, we generally have a right rag bag of assorted chillers from all sorts of different decades. Chiller has two sections. The first section is the evaporator, and what the evaporator does is it gets cold and supplies chilled water. The chilled water goes out on the chilled water header. That's at the top there, that's the blue for cold. Goes off to the zone heat exchangers, and then it comes back from the zones, and of course it's warmer now. We typically control to chill water return temperature. So we try and maintain the chill water return temperature to, not too high. Sometimes we control to chill water supply temperature, and we'll control that to about 5 or 6 degrees Celsius. We have a chill water pump that pumps the water through the chiller. Okay, so that's the chill water circuit. Chill water supply header, chill water return header, chill water pump, through the evaporator, and then the zone heat exchangers. Each zone typically has a chill water valve, and the chillers, if we have more than one chillers, we typically have an isolation valve on each chiller. The other side of the chiller gets hot. This is the condenser. The condenser gets hot. We pump water through the condenser using the condenser water pump into the condenser water header. That hot water, because it's hot, it's come through the condenser, is sent off typically to a cooling tower on the roof, where we cool it down through evaporative cooling. We run that cooling tower, we run the fan on that cooling tower using a VSD, so that we maintain a condenser water leaving the cooling tower, a pond temperature, and that is the condenser water return temperature to the chiller. Okay, so we maintain that so that I think we're maintaining it sort of 30 odd degrees Celsius, condenser water coming back, maybe 25 if we can get it. There's a whole video on cooling towers where we talk about the cooling tower, its approach, its efficiency, its range, and that sort of thing. Of course, a cooling tower can only work if evaporation can occur. And evaporation will only work if the humidity is not too high. So basically, on this chart, evaporation works in the green, the greeny blue, and the yellow area. Up in the orange areas, Carnarvon, Port Hedland, Broome, Darwin, Townsville, Rockingham, cooling towers just aren't going to work. So you'll need air-cooled condensers, which are nowhere near as efficient. And the best place to put those is on the roof, which unfortunately is also the hottest part of the building. How could anyone ever imagine unquiet slumbers for the sleepers in the quiet earth? La fin.